Good afternoon. So in last class we have discussed about X-ray diffraction techniques, X-ray X-ray absorption technique, X-ray fluorescence, as well as grazing angle X-ray XRD. So those basically based on X-ray diffraction techniques. Mostly we use for like powder XRD. We do mostly the powder X-ray diffraction studies of powder sample, then grazing angle XRD for thin film. Studied analysis of thin films like for solar cells, all those type of thin film structures, and then we discuss single crystal XRD for single crystal samples, and this synchrotron XRD that is almost similar to that of conventional XRD. Only the difference is on the source. The source is from synchrotron radiation of highly monochromatic X-ray with high brightness and flux that we are used. So today we will discuss small angle X-ray specifically we discuss scattering techniques like diffraction. Like diffraction is a subset of scattering. In diffraction, if you see, we are using the wavelength that lambda is about 1.54 in case of copper, 0.07 in case of molybdenum. Those are equivalent to that of lattice spacing. So that's why we are getting information about this crystal structure, all those information. But today we'll study the scattering technique, which is mostly useful to measure the particle size, particle shape, and its porosity, or all those information you will get from small angle X-ray scattering technique. And afterward, if time permits, we will discuss the remaining part, that diffraction technique, the Newton diffraction technique that I could not cover in last class, that we'll discuss. So when you go to this small angle scattering techniques, if you see, the small angle means your angle is very, very low. So it's almost parallel to your the plane. That you see, the angle is very, very low in this case. That we will discuss today. So if you see the X-ray or neutron, if you see, you can see this image that mostly that this structure, this whole wavelength, if you see from 1 angstrom to 1 millimeter. So mostly optical microscope, light scattering technique, those use micron size particle. In this region, you will able to use microscope, take optical microscope or light scattering. If you go to transmission electron microscope, TM, or those things, here you will see particle size up to 1 nanometer to 5 nanometer. In that range, you can see the particle size up to this range. And if you go to X-ray diffraction, electron diffraction, they are mostly usually see angstrom level interference effect. So mostly the molecule, that microscopic length scale, we are able to see this diffraction techniques, and this macroscopic length scale that use in this microscope, optical microscope, or light scattering, that is dynamic light scattering. If you see the DLS or TM that you can use, or SCM you can use. But in between these two, that 1 nanometer to some micron, like 500 micron or so, in this range, that most we use mainly two techniques. That is, one is SAX, that is small angle X-ray scattering. Another is SANS, that is small angle neutron scattering. So that is used to see those micellar structure, nanoparticles, protein, polymers, nanotubes, if some precipitate, all those nanocomposite, all those structure, shape, structure, all those things, you can get these two techniques. So here in both the techniques are almost similar. They are complementary to each other. And principle wise, if you see, they're almost similar. But in case of small angle X-ray scattering, you are using X-ray, that X stands for X-rays. But in case of SANS, it is a neutron. So here you need, for neutron, you have to have a nuclear reactor. From there you can use the neutron source. But in SAX analysis, the conventional, you can do it in any conventional techniques. Okay, so if you now see that why we need a scattering pattern, why, first of all, why you need a scattering technique? Because if you go for a TM analysis, or like SCM analysis, or all those things, you have to proper sampling. The most important thing is sample preparation. But in case of scattering technique, it's a very fast and a meaningful global average. It will give you a average out result, that instead of getting a, like for a SEM or TM, you only see this particular area, what is the microscope will focus, and there you will see the particle size. But in case of scattering technique, the whole system that will take that, that diffraction or a scattering pattern, and from there you interpret using various software to get this, meaningful result. Instead of a small area, you will get a global average information and can be proved, 3D structure like something inside the surface. So those information you can get from this, and it's a in situ and non-destructive technique. It can be used specifically if a liquid sample, and if during some transformation, some phase change, some how the shape change or how the morphology changes, those information you can get. But this main disadvantage of in microscopic thing, if you can see directly, you can see the particles, you can measure this, you can, yeah, just 1 minute. Yeah, you can measure the particle size directly. If the scale is 50 nanometer, you can measure this is about 40 to 50 nanometer if diameter wise, you can see easily. And these are the 50 microns. So the 50 nanometer scale, the spherical particles about 30 to 40 nanometer in the range. So directly you can prove. But here, in case of science, if you see, so there you have to interpret the result. It's very hard to interpret the data. You need a particular data set, that's the model. That model has to fit and to get the data. But microscope, though it is very easy to get, but some buried information that you can be able to see in the scattering technique. You see the difference between small angle scattering and microscope. So microscope use lenses. If you see, this is a microscope. This is a microscope technique in which the incident beam falling on the sample, then you have to focus and get the image. But here that you use a lens to resolve the directly in the real space image of the sample you will get. But in case of science, what you get, or you like the small angle scattering, you combine that xi or n, you silent that small angle technique. If you see small angle scattering technique, so there you see you will get an image from the Fourier space. So it's mainly see the incident beam falling on the sample, then it's scattering here. So here what you are getting an interference data. So this is your incident beam is interacting with the sample, and you are getting an interference in the wave structure. So what you will get, what the result will reach in the Fourier space. So you have to Fourier transform, then average out what are the volume you expose. The incident beam is exposed to the volume. Okay, so then you will able to get the information. So here the small angle scattering, whether it be neutron scattering or X-ray scattering, both are used to characterization of nanoparticle that will give two information. That is, one is shape and size information you will easily get, and you also get the dynamic information and probing interaction among the molecule. If there is one molecule here, another molecule is there, whether it is like how they interacting. If you have imagine a solution, that solution containing a dilute solution or a concentrated solution. If a concentrated solution, the interparticle interaction, the interaction with the particle, and the dilute solution interaction among the particle will be different. So those particle interaction that you can get in, or molecular interaction you will get, and you will see the self-assembly structure like a surfactant molecule. That surfactant molecule can be assembled, like if you see, this is just a surfactant molecule, and this surfactant molecule can be aligned to get a micellar structure or reverse micelle, or this type of micelle structure you can get, or you can get a reverse micelle structure, or you can get a like some vesicle structure, vesicular like liposome, some vesicle double layer structure. But those information that how they assemble to get the structure, that molecule, that surfactant molecule based micelles, that vesicles, all those information, whether it's a rod shaped vesicle or rod shaped micelle or elongated micelle, or it's a spherical micelle, hexagonal micelle, all those information we get by this X-ray technique, small angle scattering technique, and it can investigate the multi-component system. These are some of the important things. But if you see the basic of the neutron and X-ray scattering, you can see this is an image of X-ray, I will say. So this is the in X-ray. If this tree you want to show by X-ray scattering, so what you will get? You will get the structure of the bone structure. So bone means it will get the stem and all those things. So that information you get. That like X-ray, we use our own medical X-ray, we will able to see only the bone. in that case, we can't see any tissue because X-ray being is highly penetrated, it easily penetrate through the low jet material like tissues, and all those are made up of carbon, nitrogen, and oxygen, those type of light element. So where your X-ray can easily transmit it, so you will not able to get the information. So only information you get from that bone that's made up of calcium hydroxyapatite. Because of hydroxyapatite, those are more calcium high-jet material in comparison to carbon and nitrogen. So you'll able to get that stuff. So X-ray will give your bone structure, but if you go to the neutron scattering, so neutron scattering will show you the leaf structure. For this tree, you will able to get both bone and leaf, both structure you are able to see in this case. So that means sensitive to very low jet material neutron scattering. So that neutron can locate low jet element where X-ray fails. Like for example, carbon, hydrogen, nitrogen, oxygen. If you want, you will not get any information in X-ray scattering. But in neutron, you will able to see that thing. So here you have a plus bone and plus leaves. So both information you will get in this case. So if you see the Newton scattering, that mostly if you see, so scattering is due to the nuclear interaction. So the nucleus is a very small and electron is moving here. So it's a tiny nucleus. So whatever the neutron is coming, so that neutron come closer to the nucleus, and then you see the nuclear interaction. As I discussed in the first class, the nuclear interaction is very less. That expressed in terms of barn nuclear interaction, so that is very less because of the very small size of nucleus. And one is your nuclear interaction, and other thing that is magnetic interaction. Since a neutron, that is a magnetic in nature, and magnetic interaction due to unpaired electron it has. So with the unpaired electrons, the neutron interact, and you will get that magnetic information also. And in case of X-ray scattering, the scattering is mainly due to from the outer electron. So nothing is correlated to the nucleus. So with the electron, this is the nucleus. So with the electron scattering is nothing but your X-ray scattering. So the small angle scattering mainly use X-rays. Small angle X-ray scattering uses X-ray, that is electromagnetic radiation. It is based on electron density. Like here in bone structure, you say calcium, as I told, if high jet material or a low jet material, so depending upon that electron density, your scattering will vary. But in case of science, it's a small. It uses neutron particles. So that neutron particle is independent of electron density. It depends on a terminology called scattering length density. The scattering length density is mainly the zone from where that you are getting the scattering from the molecule. So that is the scattering length density that you will able to use in case of neutron scattering. If you see the history of small angle scattering, so there mainly the Gunier first, 1930, he predicted this method and introduced this method. Then 1930 to 50, Gunier and other, they developed, fundamentals theories of small angle scatterings. And then first experimental was with protein in 1950. With protein sample, the protein structure analysis was performed with this small angle scattering techniques. That it's very user friendly and beamline that adapted method. It's you don't need any high energy source or synchrotron source here. So with the conventional beamline, so you'll able to see that small angle X-ray scattering. So on mid 1990 onwards, the number of publication increased in case of SACS. Mainly the SACS research purposes was started. Its peak is around 1940, mid 1940. So you will get all this information from the small angle scattering technique. As I told, the size of the scatterer. Scatterer is nothing but your sample, the particle from where the X-ray or neutron is scattering, what is the amount of the sample that scatterer, and what is the polydispersity. That means what is the distribution of particle size, whether particle is 10 nanometer, 100 nanometer, all those information you will get, that variation of particle size, that polydispersity you will get, and then distribution of scatterer and shape of the scatterer. You will get the information about whether it is a spherical, whether it is a hexagonal, whether it is a cylindrical, all those information you will able to get. Then what is the shape, that morphology, then composition of the scatterer. You can get some information about that. So you will see it's a technique that gives many information together. So if you see the principle of small angle scattering, then it's mainly it uses that what you measure is a coherent electric scattering of radiation a very small angle. If you see this is your sample and this is your incident beam is falling, you can see the scattering angle is very low. That is your theta. That this 2 theta is very low in this case. That you can express because of this very small 2 theta. So it's difficult to exactly measure. So instead of that, what you measure, we measure is a q expressed is a q, that's wave vector or scattering vector. That q is nothing but 4 pi by lambda sine theta. So if it's a wave vector, incident beam wave vector is k, and this k prime is the scattered one, then scattering vector q equal to k prime, this k prime minus k, that is q prime equal to 4 pi lambda by sine theta. So that you can see here, and measuring the intensity of q, that scattering vector intensity, it varies in the 0.00121 angstrom, and scattering is from 1 to mostly up to 100 nanometer particle size. You are able to get most of the information. So scattering experiments measure the number of neutron. That is, if you take a sample and you radiate with neutron or X-ray, okay, what are the number of neutrons or X-ray scattered at different values of wave vector? That what the scattering experiment measures. A different wave vector, that means a different 2 theta, what is the the number of neutrons or X-rays are getting scattered. Like if you have a particle here, and from this particle, so how that after incident beam falling on it, how they are scattering. So how they are scattering at number of neutrons or electron or X-rays scattered, that is measure a different wave vector. So if you see that relation between small angle X-ray scattering and diffraction, so you see you will come to equation of D equal to 2 pi by Q. So this D is spacing and this K is a scattering vector. If you see, so K and K prime, my incident beam is this, my transmit that after scattered beam is like this. If you do this angle is K prime, so this angle is 2 theta, this is nothing but your wave vector, that is scattering vector q, scattering vector q. So this is there, and this q can be expressed as a 2k. This k and k prime are almost equal, so 2k sine theta, that is 4 pi by lambda sine theta. So this is the q, and we know that Bragg's equation is that we have scattering diffraction to occur n lambda equal to 2d sine theta. So this equation you can express as if n equal to 1, this is lambda equal to 2d sine theta. Then this lambda equal to 2d sine theta if n equal to 1. The first order plane. So that means you can rearrange this equation, that is 1 by d equal to 2 by lambda sine theta. If you take 2 here, the lambda bring down here, and d this side, you will get 1 by lambda d equal to 2 by lambda. And so if you compare this equation, you will get that d spacing d equal to 2 pi by q. So that is the relation between scattering vector, this scattering vector q, and your d spacing d. That is common equation. And then you see what is the main structure you will measure here. That from Bragg's law, as you know, that the distance probed is inversely proportional to q, that d equal to 2 pi by q. Here we see, so that means the bigger distance, the smaller is the q. That as long as you can see here, this is a small particle, this is a small particle, is a big particle. So in small particle here, the scattering at the crystalline plane, crystal lattice is scattering. So you are measuring the scattering angle is greater than 10 degree, high angle scattering here, and you are getting d, that interparticle distance between 1 nanometer. That means bigger is the distance, you have you see in that bigger, smaller q. In this case, a big particle, you can see the scattering on the surface only, that here. So that means scattering of the particle and scattering near 0 to 10 degree, very low degree incident, and d spacing equal to 1 nanometer to 100 nanometer. You can measure by this, scattering techniques. So if you see, this is the whole structure and the whole that this whole information will get high Q, that wide angle study, that is normal conventional XRD, high Q, that wide angle, that intraparticle, intraparticle and atomic level data. This is nothing but you are getting this spacing here. If you have a wide angle, that is a conventional XRD. In this case, in case of conventional XRD, you will get this high Q data. But if you go to low Q, that very small Q range, that will give you, intraparticle distance, colloidal distribution level data, and larger structure. It's a large whole structure you determine with very low, small angles. So larger the structure, if the structure is large, and the smaller is the scattering angle. It's like, for example, if a structure is this much and this much, if you see the scattering angle, you can see here, the scattering angle will be depends that upon the structure, that is the size of the particle, that smaller angle, that if you have a larger structure, a big structure like this big structure, the scattering angle is very small. In case of other one, it is opposite way. So if you see the 2 theta variation using copper K alpha of X-ray, so if you see D and 2 theta, so 10 angstrom, your 2 theta is 0.84 and Q equal to 0.628 angstrom. But if your micron size, if you see D, that particle size you are getting, your Q is very low. So high angle X-ray scattering, usually 2 to 160, that 2 to 160 2 theta, that the atomic structure you will get. And small angle scattering, as I told, for small angle scattering, you will get the big thing structure. So that means the Q is ranging from 0.001 to 1 angstrom in most of the this small angle techniques. So angle and wavelengths are important parameter, both angle and this wavelength. So lambda equal to larger wavelength 1 to 10 angstrom in opposite. In small angle, your lambda is 0.1 to 10 degrees. So 2 theta is very low. You can see here is lambda is here, 2 theta is very low in case of small angle things. So if you see here, if you compare the whole things, scattering from a large structure, if you see neutron and X-ray wavelength equivalent to the space between the atomic crystal. Both X-ray and neutron, that wavelength is almost that equivalent to the space lattice spacing, and that you can see here, this is your wide angle XRD, the atomic structure you get mainly peak diffraction peak we are getting, that is from conventional XRD technique. In this peak you will get, but here in case of 1 to 100 nanometer, the size is larger, 1 to 100 nanoparticle proteins, so there you will get information about how the interparticle interaction, what is the shape of the particles, what is the form of particle, all those information you get in case of larger structure. So mostly it gives diffraction peaks at higher angle corresponds to the atomic position. That means fibers, polymers, surfactants, dispersion, nanoparticle, liquid crystal, biological material, all those you can use in this case. So larger the structure scattered at small angle. If you have a big scatter, if you imagine a small particle here, the scattering can be possible at a different angle, and if a very large particle, your scatter will be almost looks like parallel or something. So for a technique using small angle, uses material properties rather than atomic properties. What you see in case of that diffraction technique, what you are saying, atomic properties are crystallite size, all those how the arrangement, the information you get. But for using the small angle, use material properties mostly investigated. Okay, if you see the experimental part of this, small angle X-ray scattering techniques, so you have a very simple, that instruments are conceptually simple, that you have a source, then source you have a monochromator, then through collimator you fall on the sample. After falling the sample, it's scattered in different direction, and then there's a detector. So that detector will detect that what the X-ray is called, transmit the X-ray is coming after that scattered X-ray. So from there we get the information about the shape and size. So we have a X-ray source generator. You need a X-ray source that will generate X-ray, or synchrotron or pallation source for production of neutron. This is for X-ray mainly. This one and these three are commonly used for neutron source. Neutron. So the beams are highly monochromatic in this case. Monochromator and Chopra defines wavelength, particular wavelength, and it has a various collimating optics are there, and then finally you have a 2D detector. That 2D detector is there here. That is mostly charged coupled CCD detector, plate type. This type of 2D detector, CCD detector or any other 2D detectors are available. And then large detector provide better angular coverage. If you have a small detector and a large detector, once you have a large detector from very low angle, all the information you can get. So distance from the sample to detector and wavelength, distance from the sample, this is the sample and the distance from the sample and the detector. So you have a detector here, sample to detector, and its wavelength of the irradiated beam that will mainly determine the size of the particles or size of the material being measured. Okay. So if you see, in case of SACS experiment, as I told, small angle X-ray techniques, SSR's measurement. So once the property is reduced, you provide the scattering cross section. Like if you see a very low angle, as I told, that 2 theta expressing presence of 2 theta is somewhat difficult. So that's why we are considering a vector scale, that is a scattering factor we are talking, and the scattering intensity. If you see that a particular angle, you will measure that. This is the di by d omega is your solid angle. This is whatever the scattering is coming here in the whole zone, it's measuring. It's not like diffraction, only one particular incident beam you will measure in case of diffraction, but here after falling or scattering in a different direction is possible. And from out of that, the scattered intensity at a particular solid angle we measure di by d intensity by d omega, and I0 is the primary. If I0 is the primary intensity beam, and T is the transmission X-ray or inherent neutron scattering, and D is thickness of the material, then dE by d omega, T by d omega, T epsilon by d omega equal to 1 by T I0 dL by d omega. So in that, and then the intensity will be di by d omega will be the transmitted beam in intensity of the transmitted beam intensity at I0 incident intensity into d. The d is thickness of the material, and dE by d omega. So dE by omega nothing of the scattering scale or unit volume. So in the particular volume, the scattering cross section, the scattering from here. So what is the volume of that? The center point. So from there, the scattering cross section for unit volume is d by d omega. So specifically, the intensity will be you have to consider transmission beam as well as the intensity of the primary beam along with the scattering cross section. So SANS instrument more commonly provides reduced data of absolute unit than the SACS instrument. So SANS will give you more accuracy, more commonly provide reduced data. It will give up to software deposition. So here, if you see the theory of the this small angle X-ray scattering or neutron scattering, so you have an incoming waves. That waves are scattered wave of electron clouds. Either it may be X-ray in case of that this SACS, and it was a nuclei in case of neutron. The incoming wave, if you wave is coming here, so that will interact the particle here, and the particle either it may be an electron cloud, outer electron cloud, or inner, if it's a nucleus, and this is the electron. So it's depending upon that the incoming wave scattered from this either electron, in outer electron, so X-ray from the electron is scattered, but in case of neutron, it's scattered from the nuclei. So interference of the scattering wavelets from the material added up, many particles are there. In some substrate, if this is a substrate, you take many samples are there. There are many number of crystals are there. So what will happen? The scattering of the individual particles will be come out. Then you have to add it. That whatever the scattering interference is occurring, so that has to be net scattering to find out by adding up, and then you have to do a Fourier transform to get the proper information. So scattering profile can be described with the parameter of the scattered intensity IQ. So that IQ is equal to nothing but 1 by phi into rho into r to the power e IQR. dV. So the IQ is mainly the intensity modulated by the interference effect between radiation scatterer and different scattering bodies. Like what is the radiation scattering is different for different bodies. That they depend on the actual intensity, scattering intensity depend on the various interference effects between radiation of the scatter by different scattering. But like if a small solid, like a strong, like iron type of material or some spongy type of material, so your scattering will be more depending upon the electron density. In case of X-ray, so that you can measure. And this, if you see that you have what you get in IQ, you get that intensity IQ, that will be mostly you'll get this type of real space data. Then you have to do a Fourier transform. You can see the particle size or whatever d is here. So after that, the scattering factor IQ versus Q, which looks like this. So that much bigger the particle, your scattering length will be small. So because of that, you can measure to characterize the size of the particle. You need to a scattering experiment in which Q span in the range of around the value of Q equal to pi by d. So as you say, Q equal to 2 pi by d is Q equivalent. So Q equal to pi by d. So in that range, you have to find out that the range where you can measure the larger the length scale, as I told, the larger the length scale, low Q. You can see this is a much bigger, larger scale. So your Q del Q is low. In this case, if you see Q is del Q, that is much high. So larger the length scale, lower will be the Q value. So the theoretically, that what are the interaction, the intensity after scattering, that what are the intensity, scattering intensity. If you see the IQ will depend on the number density of the particle. Like if I take a substrate, in the substrate, how many particles, like whatever the exposed area, this is the exposed area, this is the area where how many number of number density of the particle, that how many number of particle you can say, then volume of the particle, what is the volume, and rho is the scattering length density. That is P for P is for particle, and M is for matrix. The matrix means your solvent here. So IQ equal to N, number of density of particle N, rho P minus rho M, that is rho particle minus rho matrix, and in square into V square. And there is another terminology is coming here, that is PQ and SQ. So two new terminologies coming, PQ and SQ. So PQ equal to FQ square, that interparticle structure factor. So that PQ and SQ. So PQ will give you form factor, that is interparticle. Like if a particle, there is many particles are there. In that case, there is particle-particle interaction is possible, and in between inner particle, that intraparticle interaction is possible. So within the particle, some interaction is going on. If something going on within the particle, that is called intraparticle structure factor or form factor. That PQ reflects the distribution of scattering material in the scattering particle. It depends on the shape and size of the particle. And SQ related to the interparticle interaction, that is called structure factor. How you can see here, this is one particle, this is another particle, this is another particle, this is another. How these two particles interact with each other, that is interparticle structure factor. And mostly by SQ example, is a hard sphere potential or sticky sphere. If you see the interparticle, if a light ball or a light, a sphere, the spongy sphere, that interparticle interaction will be less. With a hard sphere, you find potentially hard sphere. So they are mainly interparticle interactions. So mainly two things. One is PQ, one is SQ. That is mainly contributing to the this scattering the intensity that will be expressed by these two, either intraparticle or intraparticle or interparticle interaction. So PQ mainly intra and SQ means intraparticle. So as I told that in case of X-ray, that scattering, scattering from the atom, that we see that sine theta varies with sine theta by lambda. But the scattering intensity I, that is proportional to sine theta by lambda. It's the exact equation is not this, though you can express it as sine theta by lambda. The scattering intensity from X-ray is varies. But in case of neutron, if you see here, here, and this is for X-rays. You can see that hydrogen, carbon is very small. But in case when you go to manganese, zirconium, sulfur, you can see in X-ray scattering electron cloud is quite large. But in case which monotonous increase with Z value, it increases. But in case of neutron scattering, it's randomly varies with Z. You can see these are the random, like hydrogen is quite bigger, then lithium is smaller, carbon is bigger, oxygen is medium, then the sulfur, manganese, cesium, they are very less. So that means you don't have a dependency on the Z value in case of neutron scattering technique. So mainly SACs, that X-ray small angle scattering, use electron density, where SANs use scattering density. They are very close related, but it provide directly complementary information. So you'll get some information from neutron that can be supported, or some other, or it will give the what are the other properties that will be detected by X-ray scattering. So if you see the scattering length density that I told in case of neutron scattering, as I told, the terminology called scattering length density. The average scattering length density rho of a particle is simply the sum of particle scattering length per unit volume. That is, this is the scattering length that per unit volume, that's B by V. That means average scattering length density rho is for a particle is sum of scattering length per unit volume. If this is a whole particle, if I see, and the particle, some scattering vector are like this. So these are the some of the scattering vector are like this. That means for the main that whole particle, if this is the area of interest where scattering is mainly occurs. So the average scattering length density rho for a particle is simply the sum of all scattering length per unit volume. But if you see for hydrogen, you can see 1H is which is minus, is a negative sign, minus 0.37 into 10 to the power minus 12. The scattering is negative in case of hydrogen, but in deuterium is just one proton extra, but you can see it is positive. So negative, and in this case deuterium is positive. A carbon is about 0.6 and sulfur equal to 0.2. Like, so scattering, if this is the scattering, you can see that length that is independent, it's randomly varies from hydrogen to sulfur. So as you see here, in hydrogen and deuterium, they have one case, it's negative in case of hydrogen, and deuterium case it is positive. So as they have different sign, by manipulating the H by D ratio in a molecule or its solvent, one can vary the contrast. So contrast in the sense, for example, if you see, if you put some in a water or oil, you put some this iron rod or something, you will see like refraction principle, you will be able to see slightly tilted, and they depending upon the concentration, all these things. If you tune in such a way that a particular ratio of H and D mixture, like hydrogen and deuterium mix it, and particular concern, what you will see, it is inside the solution, you will not able to see that iron rod. So that is something called contrast. So that equation, as I said, that IQ, that mainly that intensity of the Q vector, that scattering vector Q is proportional to rho P, rho particle minus the rho medium. That is nothing but is called contrast factor. What is the density that rho P, that scattering length density of solvent, and part and scattering length of that solvent means matrix here rho M, and rho P the particle. So from there rho P minus rho M, that whole square is equal to a contrast factor. So that can be varied, that contrast can be varied, that del rho, that is rho P minus rho M, that is nothing but del rho. So this can be very depending upon the ratio of H and D. And zero constant means no small angle scattering. If this particle and the medium, they have contrast is same, then what will happen? You will not able to see any difference. That case there will no scattering is possible. You can see here on example I have shown. So this is, you can see that here making invisible visibly, something is here, so that you are not able to see. So IQ equal to N V square rho particle minus rho matrix into PQ. Yeah. PQ into SQ, that interparticle interaction factor and SQ factor is there. You can see here that is something is not visible, but you can make it visible. Like I have given here some particular pink color. That means I have been giving some contrast difference. So my rho P, initially my rho P minus rho M was 0. You are not able to see that. If there is a contrast difference between this, you can able to see. For example, if you have a core cell structure like pink core with blue cell, so you can adjust this contrast by varying with this thing like deuterium and water concentration, that rho P minus rho M. You will able to see that core. Here you will get core information. Here you will get cell information. So solvent matching, that is called, if you are solvent matching particular solvent you take, you are matching the scattering density of the molecule with the solvent, facilitate the study of the component by rendering invisible another invisible. Like for example, you have to take the cell matrix. If you have a core cell structure and that and if you have a core cell structure, in that core cell, core and cell is here. If your the cell contrast is equivalent to a solvent contrast, then you instead we will not able to see the cell here, say here only core. In the other way, you will see the cell. By simplifying this thing, by varying the contrast, you can able to see the multi-component structures. So if you see, you can see here this example, I told a glass rod in a water. Here you can see the glass rod depending on the refractive index variation of the glass and the water. But the right side, the glass rod, if you immersed in a particular oil, that is a refractive and the same to that of glass rod, here you are not able to see that glass rod here. So here del rho, that means that the refractive index, that del rho is 0, that then you are not able to see that that image. So optically you will make it invisible. So similarly you can see the core cell structure like that. So if you see in SANS, the contrast factor, if you see that you can see rho P minus rho S whole square, that is your contrast factor. So IQ is mainly based on this equation. The IQ is mainly depend upon this rho P minus rho S. So here you can see the core cell structure, there is rho solvent equal rho core equal rho cell. Everything is different here. Then you can able to see the core and cell and the solvent here, everything. So if solvent and core are same, so you can see that here and here only red color you are seeing. So the core and cell is only visible, other thing. The third one, the solvent and cell are same, that cell you are not able to see, only core is you are seeing. So by varying this, the whole thing will depend upon the how HD ratio varies. So some of the one example I have shown, typically the contrast matching, you can if a molecule AX, BY, the sample that concentration, that rho scattering length of whole material AX, BY equal to X of rho DTO minus 1 minus X plus 1 minus X of rho of water. So scattering length of your water and DTO, by varying that, you can able to see the structure. You can see the experimentally here that in a 1% silica at different concentration. This is 1% with that scattering intensity with Q. You can see that a particular in this point, what happened, that the ratio of water and DTO mixture, here you are not able to see that it's going to the crossing point. You can see here, this one water is 50% here, water is 25%. You can see in this 25% here, peak is that it varies like this, and then you can see it's going to go straight line. So the particular concentration where that rho SI, if you keep 3.81, you 10 to the power 10 order, that contrast mismatch point where 60% D2O, that beyond this that you will not able to get any signal. So up to 50% you are getting some signal, that but beyond that one thing. So you can find out this by varying the D2O contrast. So next is the small angle X-ray scattering, that there it is a scattering length in case of neutron, but in case of small angle X-ray scattering is electron density. You can see how the electron distribution, that Z is depend upon Z. That means IQ is proportional to del rho square here. The rho is equal to the rho of particle minus rho of matrix. So this rho here is NE by M into D. So that is then the Avogadro number that into molecular weight into density of the material. So if you calculate for water, any the number of molecule that is there. So 10 by this 10 numbers are there, so you can calculate that row of water is here. So here row particle is not equal to node matrix. You can see the whole image you will able to see. But if row particle is equal to row matrix, then in this case you can see only this red portion, you are seeing all other is mismatch. That means that electron density is almost similar to that of matrix. You can see that things. So contrast is caused by here molecule composed of different atoms. That means you have a hydrocarbon in water or a some molecule but different densities like crystalline amorphous region. So that differentiate will be very in case of electron density. If you simply see in a transmission electron microscope, you compare example like core cell structure. As you know, if this is made of your zinc oxide and outside is your silica SiO2. If you have seen some TM image, that core will be highly dense and this will be lighter in region. So this is because the high Z material, the contrast is different and cell contrast and core is different. You can able to see the core cell structure in mass contrast way in case of transmission electron microscope. Similarly, depending on the electron density, you will able to see the SACs, the small angle X-ray. But the information you will get from science and SACs that we will discuss after 2-minute break. If there is any question, you can put in the chat box. You can ask also. Okay, we discussed so far about the small angle scattering, that is instrumentation principle, all those things we discussed. It's mainly and how the contrast factor importance for the small angle neutron and X-ray scattering. So as you discussed that depending upon the solvent, that the matrix and the sample contrast. So you can tune in such a way you will get, like for if you take a micelle structure, like a micelle is formed and the micelle on the head, that is surface, is nothing but the composed of spherical structure of the aggregated structure of a surfactant molecule, and the surfactant molecule, if there is for example you take CTAB or SDS like CTAB, that you have a sodium nitrogen atom is there, acetyl butane like CTAB, DTAB, or if you take sodium dodecyl sulfate. So most of this you will get some anion species there, chloride or iodine or bromine, those type of species are there, and their bromine for example, so that will high electron density compared to that hydrophobic chain that is composed of carbon and hydrogen. So that means you have the difference between electron density of the this end group, that and that head group and your tail in that tail there. So because when you have a structure like that, you will get information from the using Sands and Sachs with a particular solvent you have to take. In case of Sands, whether it's a neutron with a D2O and water mainly in case of Sands, and then you can tune such a way so that rho particle minus rho m difference you will matches such a way you will take the core and cell structures. So in general, the information you will get, that if you see the equation, the scattering intensity IQ here, that nothing but n into v square, that n equal to number density of the particle, and v is the volume of the particle, and rho, that rho is nothing but your rho particle, that rho p, the scattering length density of particle minus scattering length density of the medium or the solvent into PQ and SQ. So this PQ and SQ, the PQ is your intra-particle interaction, so like within the particle, what is the interaction? So that will give mainly your form factor, and then another thing that depends on the shape and the size of the particle, whether you have a cubical shape, whether it's spherical, whether it's a hexagonal shape, the form factor, that PQ will mainly depend on the shape and size of the particle. That means it will give you shape, size, and distribute. The information you will get from PQ is shape, size, and size distribution you will get. And the SQ, that is interparticle interaction within the particle interaction. Like these are the particles, so how this particle interact with this, how this particle interact with this. So that and then it's average out whole things, that interparticle interaction you will get SQ. So that will give interaction and ordering of about the sampling, and then sample and the shape size mostly you get from the form factor. So the number density, volume fraction you will get from N and V, and composition information you will get from the scattering length density. So this is basically the information you will get from Sands and Sachs. If you see, if you take this, for imagine a system that is diluted, another system is concentrated system. If a diluted system, that means number of particles here is less. When a number of particles here is less, you can see here when a number of particles, so this is SQ is your interparticle interaction. So the PQ is your intraparticle interaction. That means when the dilute concentration, so that SQ, that second term, that interparticle interaction will be less, because the particle-particle interaction will be less in this case. If three particles I have shown here, 1, 3, and 2, if this is your 1, 2, and this is 3, there is here 1, 3, 1, 2, and 2, 3. So there is the interaction will be only three type of interaction is possible here between these three particles. So that PQ factor will be comes into picture here. So particle size and shape, that will give because the form factor. But SQ, that interparticle interaction will be less in this case, because it's whole thing is highly diluted here. So IQ is mainly depend upon the concentration, that the intensity increases linearly with the particle number. So if the number of particles is more, then what will happen, that the SQ factor will come into picture, the intensity will increase linearly. But if there is one diluted system, mostly it's a PQ dominant system, you'll see. But if a dense system, if you see that the numbers of particles is much higher, the distance between the particle is lambda, they are very close to each other. If you see the distance between the particle, they are very close. So interparticle interaction cause the structure factor, mainly dense system like amorphous material. So all type of dense system, what you see, so that there the structure factor will be mainly dominating in case of this. But when you have a density, you see the other thing, the liquid crystal structure, which is hexagonal. If you see here, it's one particular particle and the lattice position, you will see the liquid crystal, you see the interparticle interaction here, that will be dominant between the particles close to each other. So you'll see intraparticle interaction causing structure factor. Information will get that will be predominant. So basically the two things you are getting, one is your PQ, then is your SQ. So PQ is nothing but your intraparticle interaction, and SQ is your interparticle interaction. That PQ, as I told, PQ will give you shape and size, and SQ will give you interaction of particle. So if you hold intensity, that IQ and Q versus particle, if you break into PQ and SQ, the PQ, that shape and size, it will symmetrically, it will decrease like this type of curve you will get, and in case of SQ, it will, this is exponential decay type curve you will get. In SQ you will get a peak, and then there is a wavy structure. So this is nothing but your interparticle interaction. In a dilute system, if I told, in dilute system mainly PQ will dominate, that intraparticle interaction will dominate. So here you will get this exponential decay curve. But in case of SQ, that constant particle, this factor SQ will dominate, that you will get the constant system, the SQ effect will come into picture. So the information what you get, so after getting this that type of spectra, so this is nothing, you will get, depending on the peak, you will get the information about that interparticle interaction. But in shape and size, how you determine in case of this type of system, that if you get a PQ factor, form factor, so there you can determine that, see the decay curve, you can see whether it is proportional to that. In this area, if you linearly, if you fit, and you see whether it's proportional to Q to the power minus, that is minus 0, Q to the power minus 1, that then Q to the power minus 2, that is independent here, minus 2, depending upon that. If it Q to the power minus 0, that means it's almost symmetrical, so it will give spherical particles in that case. That is size information, that mainly in case of spherical, so size you will get whether is elongated, like a low Q region, the Q to the power minus 2, minus 1, that will be mainly, that's, you will get the size information from here, and then you will get the shape, whether it is spherical here. If you fitted that spherical with the rod shape, you will get that Q to the power minus 1, and if it is Q to the power minus 2, you will get a disc-like structure. And low and surface area information also you'll get in very low Q region. So there is 3 regions: Gunnier region, Fourier region, and Porrard region. Porrard region, Gunnier region will get the size effect, and in case of Fourier region, you'll get the shape, depending upon the Q to the power minus 1, minus 2, or minus 0, or in this low Q region, you'll get the surface area information. You can see here that in spherical case, it's Q to the power minus 1 here. Q to the power 0 will be fitted to this, and in case of it is in here only fitting, and Q to the power minus 1 here in this case. And in case of rod-like structure and ellipsoid or disc-like structure, you will be, if you fit it here, it will be Q to the power minus 2. So depending upon this data, the Q dependence of PQ, you can find out by using software and fitting. You can find out what is the shape of my particles. That information you can get. And another thing you can also get, that is called pair correlation function analysis. From this, whatever the IQ, if IQ image you are getting, that IQ or PQ versus Q factor, from that intensity, you can, with respect to distance, if you plot, like this is the whole molecule I have, and within the molecule, that is the maximum distance D, can you measure from this to this, is a protein structure I have shown. So this to this distance, and in between that, I want to find out a small area vector, how my particular element or particular unit length or some particular molecule or a molecular length that is varying, probability of finding this small r in the whole D max that will nothing but your pair distribution coefficient. That is probability of finding a vector of length r. If this is my a vector, I am talking like for a protein, you see the composed of many amino acids. So I want to find out the particular amino acid, things, so that how that molecule is repeated in the whole structure. So the probability of finding that small vector r in the whole, scattering length, the molecule can scatter from anywhere. So out of that, how much is scattering from this area, my particular area of interest. So that I can find out by pair distribution function. That is nothing but the inverse Fourier transform of scattering function to real space. This is my intensity versus distance. If I see here, after Fourier transformation, I'll get this type of a symmetrical curve. From that curve, it provides PR provide that real space interpretation of IQ. You can see here, if I do a Fourier transform of the pair distribution function, you will see you can get the red one here. You can do highly symmetric curve you are getting. That is for spherical set particle. If a rod set particle, I will get this type of initial increase and decay. If it is a double core cell structure or a double disc structure, you can see in the two double dumbbell structure, you can see two peaks I am getting, in a disc I am getting, though it's a symmetrical, but it's it's not perfectly symmetrical to that of a spherical one. And if you have a core cell structure, depending upon the signal intensity from the core or cell, you will get this type of peak. So from PR provides the information about the shape of the particle, so that you can find out the by calculating the probability of getting a particular that vector of length r in the whole scattering within center. That you will able to get, that will give you information about the shape. So once you get the small angle X-ray data, so that directly you can't use it. So that data has to interpret it. So for that, that interpretation is quite difficult. So you have to use different models, available models in the literature, whether depend that is for cylindrical, core cell. So different structure has a different type of model. So first you have to select a proper best possible model, then fit your data using the selected model. If fix values like known physical parameter as many as possible. If it is fit properly, good fit, okay, it might be a possible model. From there you can get a core cell like structure or the length, or if it is elongated structure that major axis, minor axis can get. If it doesn't fit, again you go back and change the model and then fit, and from the fitting you will get, once your final model is fitted, you will be able to get the results, and that has to be supported by complementary technique. As I told, that whole small angle X-ray or neutron scattering, the whole data is based on the interpretation, and it's based on the model fitting. So you have to always complement the data with other technique. For one example I have shown here, you can see here, this is a block copolymer, that P85, that is ethylene oxide, propylene oxide, and again ethylene oxide. So 25, 39, and 25 units of EO. So it's this is initially hydrophilic. This is hydrophilic. Then you have a hydrophobic zone. Then it's a hydrophilic. This is hydrophilic. And this is hydrophobic. And then again hydrophilic region is there. So if that from a micelle, you can see that which is a rod-like micelle or a unilamellar or a unimer. You can see in case of unimer, here you can see it's go like and this type of that Q dependence you can see here is a unimer that freely starting here, but when you have a rod-like micelle, Q to the power -1 in that case. So you can able to see the rod-like micelle. In spherical, you can see Q to the power -0. So in that case, unimer and monomer structure. So the low scattering at low temperature, like how the temperature at low temperature is from a surfactant. Then the scattering increases if the low scattering at low temperature is from a block copolymer dissolved as a unimer, and once micelles are formed, the structure of function of temperature. So depending on the temperature, how the structure changes from spherical to rod shape, that information you can get from using a SANS data, and then using the SANS data you can calculate that after proper model fitting. You have shown that SDA, CTAP. So these are the structure in that model fitting when able to get the minor axis that or major axis length and aggregation number, all those parameter as well as polydispersity, how the distribution of the different molecular micelles size, that information you can able to calculate from the after the theoretical data you get. So experimental data and model, that black line here in the green is the model fitting. So the fitting parameter you can get all those information. So another example here you can see here, this is a ferrofluid that Fe3O4 nanoparticle with some surfactant coating on the double coated surfactant molecule. The inner layer is the outer layer with DTO water mixture, and this is the SANS data here, how the scattering intensity varies with Q, and you can see the only size of the ferrite. Like if you take Sachs measurement and SANS measurement, the difference is here. Here is the center is Fe3O4. That Fe3O4 is high electron density compared to that of surfactant, carbon, hydrogen. So when you go for a Sachs information study, you will get the information about the core. Only size of the ferrite particle you will get a core diameter about 4.8 with particle distribution. We have got a 50%. But when you go for the SANS study of this ferrofluid, this particle in iron oxide particle solution, so what you will get in SANS, you will get the particle size and thickness of the surfactant coating. So that means you will get both core information as well as cell information. Both information you will get in case of core as well as cell structure you will get, and that you can confirmed by using a dynamic light scattering study, DLS. The DLS will give you overall size, the whole size you will get in case of hydrodynamic diameter that you will get in dynamic light scattering. So you can see you are getting up 10.45. So if you say core and cell, if you added, you will get like this is about 4.8 and around 8.8 you are getting, here is 10.5. So you have to confirm your data with some supported with other technique. So this way you will be able to calculate that all this structural information. So if you see the SANS and SACS basic difference, what information you will get. So if you have a CTAC solution, like signals can assess the contrast between the solvent and the hydrocarbon chain in the core of the micelle. Like if you go, so that if you have a micelle structure, that core, that whether it's high in the head group has a bulky, that high density molecule there. The sacs are sensitive to the inner structure of the polar cell because of the electron density of the head group. Like if you have a micelle is formed like this, if a micelle is formed like this hydrophobic micelle or something, you can see here the sacs are sensitive to the polar cell. That is the head unit. Head is hydrophilic. The head is made up of some polar molecule with high jet, little electron, chlorine, nitrogen, or those type of molecule there. In case of CTAP, bromine is here. In case of CTAP, those type of things. So what you will see, so you will get this is mostly this X-ray dependent, depending on electron density. So head group, the counter ions and penetrated salts are higher than those of the solvent and micelles at the core. So here hydrophobic, that tail will be outside, so that will be made of carbon. So if you see that CTAC and CTAP, that cetyl will be ammonium bromide or ammonium chloride. If you will take CTAP and CTAC, the contrast variation you can see. If you go for a SANS measurement, what you are getting the whole average, only one peak here. But in case of SACS, you are getting, see, two peaks are coming. So that means that the outer, the head group, that information you are getting here in case of SACS. So that information will get. You can see in a CTAP, when the chlorine is replaced with the bromine, you can see they are almost split into two peaks. So the additional information will get in SACS in comparison to SANS also. So those type of both information you will able to get. And the whole thing, as I told, to do the SANS measurement, the SACS measurement can be done in any small angle X-ray scattering unit. That's mostly there are many available instruments like Anton Farr and some other companies are there. They are doing the small angle neutron scattering X-ray technique based any companies. So they are giving, but in case of SANS, you have to develop with the help of a neutron source. So you need a neutron source to get that SANS measurement possible. So like in BRC, you have a SANS facility at BRC that is it's available nationwide. So anybody can access this SANS study by sending the sample to the, if anybody interested, so they can mail me. I can associate them with a specific group who can help for the SANS measurement. Like this is the beamline that available in case of Dhruva reactor in BRC. It's a vertical type tank type reactor, and here if you have a monochromator of the wavelength is around 4 to 10 angstrom in the range, and Q range that you can measure from very, very low 0.015 to 0.5 angstrom was that you can use here. So basically, if you see that SANS and SACS, that is this SANS study, although it will take quite a longer time, like neutron scattering, that you have to scatter from the spiny nucleus, you have to do scattering measurement because for longer time to get the results. Okay, so I will now discuss that another technique that neutron diffraction that I could not cover in last class, that like as I told, scattering and X-ray scattering and neutron scattering I discussed. Similarly, X-ray diffraction I have discussed. This another one is neutron diffraction. So neutron diffraction, it also satisfies whenever the Bragg's law, the neutrons can diffraction will occur. So that we will discuss the neutron diffraction right now. So I'll just share the other PPT to discuss the neutron diffraction. Okay. Can you share that one? If any question, you can ask right now, or you can raise the question here. So, yeah. Since there is a similarity with neutron scattering and neutron diffraction in the neutron part I could not cover last time. So now today we'll discuss the neutron diffraction. So similar to X-ray diffraction, it follows the it follows the Bragg's law. So I have already discussed these things, basics of neutron scattering. As you know, the neutron scattering, you have two types: that nuclear neutron scattering, then there is a magnetic neutron scattering. Since it's a magnetic moment, that structure factor will say in case of X-ray, it is mainly that X-ray the scattering from the electron. Here you have a contribution from the nucleus, the Fn and Fm, that magnetic contribution from the electronic part. So neutron with thermal energy mainly 10 to 100 milli-electron volt, that is mostly used in neutron diffraction studies, is comparable to the atomic space. The wavelength, if you see, is for 2.86 to 0.99 angstrom. So that is quite close to the atomic separation. Like in X-ray, we are using wavelength about 1.54 angstrom. In case of here is about 2.86 to 0.9. It's quite close to the to see the inner structure, like some crystal structure of the material. But the advantage you will get in addition to the crystal structure, magnetic information, you will also get in neutron diffraction. If you see the instrumentation part is almost similar to that. You have a reactor source. From the reactor source, the neutron beam is coming, and then the neutron is falling on the sample surface, and then it's going to diffracted beam with the detector. So you have an angle 2 theta here. So that is similar to XRD, but different in the type of radiation used to give a complementary information. So neutron diffraction is sensitive to the atomic and magnetic structure of the crystalline solid, gas, liquid, amorphous material. So all those information you can get. If you see the neighbors, the X-ray diffraction doesn't tell anything about isotope. the neighbors and isotope can't be discriminated. If you take a X-ray from copper and zinc, that is close, so it's difficult to interpret little bit. Sometimes like if there is no difference in crystal structure, then it's fine. Otherwise, it's quite difficult. So neighboring and isotope can't be discriminated in case of XRD. But you take neutron diffraction, like carbon 12 and carbon 13, or some other isotope you take. So those, discrimination can be done, and the light element is hard to detect in case of XRD, like carbon, hydrogen, nitrogen, you can't able to detect in case of XRD. So that information you can get from detected from neutron. A magnetic properties also can determine from XRD, which you can determine from the neutron diffraction. You have a but the only problem is there is a lower availability of the neutron diffraction techniques, that since you need a nuclear reactor, but in case of XRD is highly availability, and very low time you can get an X-ray spectrum, but in case of neutron diffraction or neutron scattering, you have to need a long time scattering because of the tiny nuclear size. So if you see the neutron diffraction, the scattering from nucleus and scattering from magnetic moment both are occurring. If you see, this is a coming and the center is the nucleus, and the neutron is interacting coming from the nucleus here. That is following the Bragg's law, n lambda equal to 2d sine theta. You will get able to that. You will mainly get the crystal structure information, structural distortion, charge order, all those information you will getting from the nuclei scattering. But in the magnetic scattering, that in magnetic scattering, that can be Q, this proportional to the magnetic field, the parallel to the magnetic applied field, or this perpendicular to the magnetic field. Q you will take. In case of perpendicular, you can see here that if there is an ordering, so the neutron scattered from the Yeah, the neutron scattered from the components of the magnetization perpendicular to the Q. When the magnetization is perpendicular to the wave vector Q, so that case you will get that magnetic scattering. So that Q is nothing but your force by lambda by sine theta. So what information you will get? The magnetic information, that is spin arrangement in ordered phase, as well as magnetic form factors. So all these information you will get. So as I discussed this already, so neutron, if you see the structure factor, that in case of this X-ray, you can see depend upon the CGM with a large high jet material, your this diffraction, that structure factor will be at will be quite high, that monotonical increases with Z value. But in case of this, that the electron density will increase here. But in case of neutron, it's randomly varies, as I told. So in XRD, that structure factor F scale, I've discussed that intensity, which depend upon Fn, that is scattering factor from the atomic scattering plus its location, e to the power 2 pi I, all this equation will get. So in case of neutron, is the scattering length of nth nucleus, the B, the scattering length in e to the power this. So being the scattering length dependent, it doesn't depend on the neutron. Now the electron, number of electron in case of neutron diffraction, you can see here in X-ray, the neutron scattering is decreased monotonically with respect to sine theta by lambda. That's why at higher angle peak, in X-ray the intensity is low. In X-ray the intensity is low. In case of X-ray, that is the intensity for 2 theta higher angle peak, it will be low intense peak. But in neutron, you randomly will get the peaks. But in the magnetic scattering will depend on the X-ray. There will be some dependence, but otherwise, if you see nuclear interaction, there is no independence of that. Scattering factor. As I told initially, that KCl, if you take KCl and NaCl, that in KCl is in isoelectronic structure, that 1-1 peak, this 1-1 peak is absent in case of X-ray, because that K and Cl, that isoelectronic, so they are arranged in such a way that they create a destructive interference. Because of that 1-1 plane you cannot able to see in the X-ray. But if you see in case of neutron diffraction, the scattering length of potassium K and chlorine, you can see one is 3.67 FM, one another is chlorine is 9.5 FM. So that if you see that big K of BCl you see there is a difference is there. So because of that, what happened, it doesn't cancel out, so you'll get the one peak in neutron diffraction. So neutron, you are getting additional peak, that information which you could not identify in case of X-ray. In case of X-ray, you see the average out, the scattering factor of K minus K of minus CL, and that divided by K plus CL is a point very, very low. So that almost cancel out, or it is there. So you'll get the additional peak 111. Similarly, another example, if you take neutron diffraction, that is Ni3Mn I have shown. So you can see here that the X-ray is very, very low, that difference. But in case of neutron, you have you can able to see that because of superstructure, you will get that additional peak, that otherwise you will able to see that information which you are not able to, that in case of X-ray diffraction. This is another example of Ni3Fe, the same thing in case of neutron, and in case of this NiFe, that is this is nickel. One is natural nickel, another is substitution nickel 60. If you nickel 60, that in this case being a nickel 60 isotope here, in that case you would see if you have nickel 60, then you have a your structure factor remains and is not null out, but here it is almost 0. So that's why you're able to see the isotopic effect, as well as other information you'll get from the XRD. You are not getting from the XRD, those information you'll get from the this neutron diffraction. Similarly, that is a magnetic samples, which are ferromagnetic or a paramagnetic or antiferromagnetic sample. In ferromagnetic samples, so they are ordered in one direction on applied field direction. In antiferromagnetic, they are oppositely aligned. So the only magnetic moment perpendicular to Q vector, as I told, that is perpendicular to Q vector magnetic moment. So that will give you magnetic scattering in case of both. If you take antiferromagnetic or ferromagnetic material, so magnetic moment are perpendicular to Q, to the scattering vector will give the magnetic scattering. So that you will get additional information. For example, if you take a ferromagnetic material and antiferromagnetic material, then normally if you go for XRD peak, so if you see the peak intensity is up to this much, and the magnetic contribution is added up to that. So because of that, the peak intensity you will see high peak intensity. The black portion here is coming mainly from the magnetic ordering. That additional information, that peak intensity increase because of ferromagnetic material in comparison to XRD. If it's antiferromagnetic material, so there is a opposite in each other, the magnetic moment. So you will get some additional peak you will able to get here in case of antiferromagnetic material. This is in the ordering. So it's a ferromagnetic antiferromagnetic material. So that can be identified from a magnetic neutron diffraction studies. So you can see this is an example of MNO, that or MNO, FEO, or NIO, if in a pseudo cubic unit cell. So you can see here it's a different temperature. This is at X-ray at room temperature, and it acts neutron at room temperature. You can see in the neutron, that is the antiferromagnetic nature, what will happen, the sum of the peak 220 peak, and that intensity is decreasing here because they are antiferromagnetic coupling each other, so that peak intensity you are reducing here. But if at very low K, if you go, so you will see some additional peak you can able to see because of some phase change, that antiferromagnetic occurring in that low temperature. So you will able to see some additional antiferromagnetic peaks, and here those information there. So those type of ferromagnetic antiferromagnetic information you will get in this type of MNO structures. So but the main drawback in this neutron diffraction is you need a high neutron flux to be very, very since very low, your experiment takes a long time, that you have to do a measurement up to 24 to 48 hours to get a proper neutron diffraction studies, and you need large scale samples. For powder diffraction, only very least quantity 2 to 3 gram can be possible, but if you have a single crystal sample, the sample size is 0.5 to 1 centimeter. But in neutron diffraction, always sample you need large quantity of sample and a longer time. And then if there is a neutron absorbing element is there, your material if you made of gadolinium, like zinc gallate or something you made, or cadmium sulfide, or some type of samarium, some alloy or boron containing sample you prepare. So those cadmium, gadolinium, samarium, or boron, they will act as a neutron absorbing. So they will absorb the neutron, and you not get proper data. So always, and the fourth, the most important point, we have to go for a major facility like reactor and spallation source for all those neutral measurements. So this I have discussed so far that in earlier class I have discussed all those XRD based techniques, single cell XRD, grazing angle XRD, synchrotron XRD, then exhaust analysis, both Xness and exhaust that both I have discussed. That single crystal XRD, it gives 3D electronic mapping, you will get atomic arrangement, and thin film XRD or depth profiling, you do grazing angle XRD, high temperature, high pressure, you can do better in synchrotron radiation in very low concentration sample or very low quantity sample, you can do it with synchrotron radiation and exhaust that how the Xness will give you oxidation state and coordination number, you can do exhaust that you can do with coordination number, and you can get bond length, bond order, all those things. And then XRF I discussed that composition analysis you can do for accuracy, with high accuracy, what is the different composition of the element that you can get with quality, quantitative also, and neutron diffraction you get the magnetic as well as atomic structure information of crystalline material, and small angle X-ray scattering and neutron scattering that I discussed today. With them you can measure the particle size of by varying the, in case of neutron you can vary the contrast by using DTO and HTO mixture, and accordingly you can get the coarser structure, micellar structure, whether it is a spherical or is a elongated or is a hexagonal structure, depending upon by fitting with that the intensity versus Q, that P, how the PQ, that is the interparticle interaction, SQ is the structure that interparticle is SQ and PQ is your intraparticle. By varying those information, by seeing those information, you can get whether from dense or dilute system, you can get the information about the all those surfactant molecules. So in the next class, we'll discuss about the electron microscope. Next two class is fully dedicated to electron microscope, and that mainly that how that SEM, scanning electron microscope, and a transmission electron microscope, that why we need a electron microscope instead of optical microscope, that we will discuss in the next class about mostly SEM and TM. So if there is any question, please ask, otherwise we will stop here.